So I think it's time to start. Good morning and good afternoon to everyone from Australia and from Asia. And the speaker today is Professor Rongchan Zhu from Beijing University. In a way, this talk will be a continuation of Martin Hayer's symposium that we had in February, because the talk is about singular stochastic PDEs and about regularity structures. So we are somewhat prepared to understand this difficult topic. Rongchan has many works on 5-3-4 theory, on stochastic quantization and other equations of mathematical physics. So we are very glad that we have this talk today. Thank you, and you can start now.
Okay, thanks a lot for this invitation, and also thank Professor Goldys for invitation. It's my great pleasure to give a talk here. And my talk is about this large n limit of this ON linear sigma model while stochastic quantization. My talk is based on this joint work with Hao Shen, Scott Smith, and Xiang Chan. And the reference for my talk is already on archive. And this paper is for concentrate on the 2-dimensional case. And this paper is concentrate on the 3-dimensional case. And my talk will be divided into the following 4 parts. Let's come to introduction part. And recall the free field in the Euclidean quantum field theory. This free field on the torus can be usually described by the following probability measure. So that means at each point on this torus TD, we put a Gaussian measure here with this Gaussian density, which written in this way, and taking the product measure. And here Cn is a normalization constant, which makes this nu is a probability measure. And here phi is just a real valued field. And the formula it can be written in this way, and it can be made rigorously by using this following Gaussian measure, which can be seen as this mean zero with the covariance operator given by the inverse of M minus its Laplacian. So if we see here, this M just corresponding to this M phi square part, and Laplacian corresponding to the gradient part here. And if we consider this measure, this is so-called this Gaussian free field. If for 1-dimensional case, for m equals to 0, this corresponding to the law of the Brown motion or the law of Brown bridge. But for the higher dimensional case, this measure in fact is not supported on the continuous function space. It's supported on the distributional space. And this free field will describe the particles which do not interact. And the physicists also want to construct some models, so-called this 5-4D model, which is the simplest non-trivial Euclidean quantum field. So the simplest way is to change the definition of this measure. So they just add this phi to the power 4 part on this exponential part, and also taking this product measure. And here Cn is also this normalization constant, which makes this one is a probability measure. And here this is so-called this 5-4D model. Here this 5-4 corresponding to this phi to the power 4, and D corresponding to this dimension. Here we consider D-dimensional torus, so we call this is a 5-4D model. And the formula it can be written in this way, but in fact, this measure is not for the, as I mentioned before, for the Gaussian free field on the 2-dimensional torus, it's already supported on the distributional value space. So for this 5-4, how to make sense of this phi to the power 4 should be a problem. And in fact, on 2-dimensional torus, this measure is absolutely continuous with respect to the Gaussian free field. But for the if we change this torus to the whole space for the 2-dimensional case, or even for the 3-dimensional case, for the on the 3-dimensional torus, this measure is not absolutely continuous with respect to the Gaussian free field. So how to make sense of to give a rigorous meaning of this measure? And to study the property of this measure should be a problem. And this has been studied a lot by from 60s to 90s by this Glim Jaffa, Simon, Feldman, Bridges. And one of the main achievements in this constructive quantum field theory is they can construct this 543 field rigorously. But today we are going to using the so-called stochastic quantization to study this kind of model. So the stochastic quantization just means we want to construct a stochastic process such that this stochastic process having this 5-4D measure as the stationary distributions. And this stochastic process can be seen as the solutions to an SPDE. And this is so-called stochastic quantization and has been first been proposed by this Paris and Wu in 80s, and first be realized by this Giuliano and Meter, and later by Avera and Rockner. By using Dirichlet form approach, later by this Taprada and Debush using SPDE trick to obtain the local repulsiveness of this the dynamic 542 model in two-dimensional case. In fact, the stochastic quantization of this 5,4D model can be seen as the following, related to the following SPDE here. So maybe there, I see so. Okay, sorry. And this stochastic quantization can be seen in the following equation. This just means we take the partial derivative for this phi with respect to time. This should equals to this here, this h corresponding to this Hamiltonian part, this energy part. We take the partial derivative of this h with respect to this phi. We get the following terms. Here, the gradient terms gives us the Laplacian part, and m gives us this m part here. And if we take the partial derivative of this phi to the power 4, we get this phi cubic part. And we also have this noise part. This is the space-time white noise, and it can be understood as the derivative of the L2 cylindrical Wiener process. And but for the three-dimensional case, how to understand this equation? In fact, I will explain later. Due to the singularity of this space-time white noise, how to understand this nonlinear term should be a problem. For the three-dimensional case, this has been opened for many years and has been first solved by Martin Heil by using this regularized structure theory, and he can obtain this the local repulsiveness of this models. And at the same time, Gubinana, Imkela, and Prokofsky also proposed this pair control distribution method, which based on this Fourier analysis. And by using their trick, Cartier and Cho can also obtain the local repulsiveness for this kind of model. And later, Moran and Weber can obtain the global repulsiveness for this kind of model, both in 2- and 3-dimensional case. And more recently, Gubinana and Hoffmanova can using this SPD, this stochastic quantization to reconstruct this 543 model on the whole space for this R3 case. And there are also a lot of other models related to this by using this stochastic quantization to study this quantum field. And today I'm going to talk about this ON linear sigma model, which can be written in the following way. Here, this ON linear sigma model, which looks very similar like this 5-4 model, but the different case is here, this phi is a vector valued field. And if we consider n equals to 1, so this just reduced to this 5-4D model here. And for this model here, this ON just means this model have this ON invariance property. That means if we change the order of this phi I and phi j, this measure will not change. So this is ON invariance property. And here, this linear just means this phi taking values in this Rn. So this is a linear space. So this is called this linear sigma model. If we consider this phi taking values in a Riemann manifold, so this is usually called this nonlinear sigma model. And today we're using the stochastic quantization to study this kind of model. And we want to study the Lagrange limit of this model. There are a lot of results for this Lagrange limit for this kind of model from physics. In fact, the motivation to study the Lagrange limit is here we can see this model when n becomes larger, it will become more and more complicated. If we want to study the properties of this kind of model, it should be very complicated. But if we let n goes to infinity, the limit may be very simple. So this will give some simplification to study the properties of this new n here. And this has first been used by Stanley for the spin glass, and later Wilson and also Wheaton also studied this kind of Lagrange limit for this ON linear sigma model. And Gross and also this also studied the Lagrange limit for the other models like this Yang-Mills model or this Fermi field. But for the mathematical result for this Lagrange limit, there are not so many this kind of result. One work has been obtained by this Copiani. Consider this ON linear sigma model, and he studied the partition function. This Cn just corresponding to this partition function. He considered the log of the partition functions and do this expansions around this 1/n here. And more recently, Chatterjee also studied this Lagrange limit of the Yang-Mills field, but with change this torus to the lattice here. And here for this new n, this kind of model, here we have this 1/n before this nonlinear part. And now we want to use in the stochastic quantization to study this kind of model. So first we write the stochastic quantization equations here. This we consider on the d-dimensional torus. And we write the equation here. By using this, we can see this part. Now the equation, since this field is a vector valued field, so the equation should be also vector valued. So we consider a system of the equations here. And here this L just corresponding to this part, because here we also have the time derivatives, and Laplacian also corresponding to the gradient part, and M corresponding to this part here. And for the nonlinear part, we just take the partial derivatives with respect to this phi I here. So we get this part here. And for the noise part, we have a sequence of independent space-time white noise, psi I here. And now we want to use in the stochastic quantization to study the Lagrange limit of this dynamic phi I, and also the Lagrange limit of this new n here. Now we recall the equation here, the stochastic quantization equation. We write it here. And as I mentioned before, here, in fact, the main difficulty comes from the noise part. So I just recall the definitions of this space-time white noise. So this space-time white noise just given by, this is random Gaussian functions, which depending on time and space here. And the covariance operator just given by here by the Dirac functions. So that just means if t not equals to s and x not equals to y, the covariance just equals to 0. So that means this is for the Gaussian functions. So that means for different space-time points, the psi should be independent of each other. But we know this Dirac functions, the regularity is very rough. Due to these properties, in fact, the regularity for the psi, if we consider the parabolic space with parabolic scaling, we can get the regularity, in fact, is in say minus d over 2 minus 1 minus space. Here, the last minus means minus kappa for any kappa bigger than 0. And here D corresponding to the dimension. We can see when dimension becomes larger, this psi will become more singular here. And we will see here for the two-dimensional case, the regularity for this psi in fact is in this C -2 minor space. But for three-dimensional case, it's even worse. And then we also recall the following result from this harmonic analysis. That means if we want to make this F times G is well defined, if F in C alpha space, G in C beta space, if and only if we need here this alpha plus beta should be bigger than 0. That means here this C alpha space just means for alpha bigger than 0, it's corresponding to the usual holder space, but for alpha smaller than 0, it's corresponding to some distribution space. So alpha can be seen as a differential exponent when alpha smaller than 0. So this just means if we want to make sense of functions times distributions, we need these conditions here. And due to the singularity of this psi, for the two-dimensional case, we can see this can be seen on parabolic equations. We have the Schauder estimate. So the best regularity for this phi I we can obtain is in the C minor space. And for three-dimensional case, it's in C -1/2 minor space. So to see this nonlinear term, this red part, if we want to make sense of this one, we can see there's a problem to satisfy this alpha plus beta bigger than 0 conditions. So how to make sense of this nonlinear term should be a problem. And also for three-dimensional case, it should also be a problem. And now for the two-dimensional case, we can using this so-called Staprata and Debush trick to understand the equation. That means for this phi I, we can decompose this phi to this yi and zi part, such that this zi will satisfy these linear equations. So zi just can be seen as a OU process, and yi will satisfy this nonlinear process, nonlinear equations. Formally, we can see the equations for this yi should, is more complicated than this equation for phi I. But if we count the regularities, say minor space. So this zi, but we know this psi the Gaussian functions, and so zi is also Gaussian. We can using this weak product, such that if, for example, for this part, if we minus the expectation of this zi zj part, and do some modification approximation, we can see the rest part will also stays in the same minor space. So we just take the rest part here. And if for I not equal to j by independence, we can say this expectation just equals to 0. But if I equals to j, we can say if we do this modification approximation, this one in fact will diverge. And now we write this equation for yi in the following way. And here the regularity, in fact, for all this weak product, it's also in the same minor space. So by using this Schauder estimate, we can obtain this yi should be in the C2 minor space. And now for each of these terms and also these nonlinear terms, every term will satisfy this alpha plus beta bigger than 0 conditions. So yi will have the better regularities. We can using the fixed point argument to obtain the local repulsiveness of these equations. So this is the Pratt-Debush trick for two-dimensional case. But for the three-dimensional case, the situation becomes even worse because we recall the regularity for this zi will becomes worse. It's in C -1/2 minor space. So if we consider this two red part, in fact, we can also using the weak product to redefine this part and this part. But the regularity now it's even worse. It's in C minus 1 minor space. And this part is the regularity is even worse. But this part we can also using the similar dot product and the Bush trick to handle it. The problem comes from this red part. The red terms are not well defined even we do this further decompositions. So here you can see if we can make sense of these terms, this one will always belong to C minus 1 minor space. By using shorter estimate, the best regularity for yi is also in C1 minor space. So how to so these terms will not well defined because it will not satisfy this alpha plus beta bigger than 0. So to understand the equation, we should using this regularized structure theory or this parallel control distribution method by higher or this could be Nana in Mikhailo-Perkovsky. But this can also only gives us a local repulsiveness. But this is enough, since for the local repulsiveness, we will meet some stopping time. And the stopping time may depending on the n and also depending on I. So here we want some uniform estimate to deduce the result. And now we come to our result for two-dimensional case. We first want to study the larger limit of the equations. And we consider, first we write the equation in the following way. And here, as I mentioned before, this red term is not well defined in the classical sense. Here we need to using the weak product to make sense of it. So here we need to do renormalization. This means we need to subtract this part. Here, since in fact, we subtract the expectation of the ZJ square part, but due to the symmetry properties, we just subtract this ZI square, the expectation of this one, to get this SPDE. And now we want to see what is the limit equations for this kind of model. And we can just see this kind of models for different phi I and phi j. These models are symmetric, so they should share the same distributions. And for this, we can see this can be seen as the average of this phi j square part. And phi j square share the same law. And when n goes to larger, the interaction should become weaker and weaker. So this reminds us the law of large numbers. So this suggests us the limiting equation can be written in the following way. The linear part, we will keep the linear part here. But this red part will goes to this mu here. The average of this phi j square goes to the expectation of this one. Since the and here this way minus this the I square part, since we do this renormalization corresponding here. And we can see for the limiting equations for this mu here, this mu will depending on the distribution of this psi I here. And it will not depending on the other component phi j. So if we assume the initial data of psi are independent, then for the limiting equation, this capital psi should also be independent of each other. And in fact, this is a distributional dependent SPDE. And here, this mu belongs to this we can also calculate the regularity. In fact, for two-dimensional case, the best regularity for psi is also in C minor space. But if we take in the expectation of this one, we can see this mu will also belongs to the C minor space. So this red part will also it's also not well defined in the classical sense. We also need to make sense of this one. And our first main result is for the two-dimensional case, we can assume if the initial data for this psi I are independent of each other. This is a very important assumption in our case, and share the same law. And also the initial data for this phi I will convergence to this psi in the same minor space. Then we can obtain for each fixed time t bigger than 0, we can obtain this dynamic phi t will convergence to this psi for fixed time t here. And furthermore, we can obtain this convergence as a stochastic process, but the convergence is only we can obtain the convergence in probability here. Not this is the moment convergence. And here, this kind of result can be seen as a mean field limit result for a singular SPD, and also tells us about this propagation of the chaos. So that means if we consider this is like some particle systems, this is the initial state. If we just assume this phi is equals to psi, and they are for each component they are independent. Now it involves with respect to this dynamics. We can see we have this interaction part. So for each fixed time t, we can see for each different component, they are not independent. But if we let this n goes to infinity, we can see the limiting equation. This means we let the number of the particles goes to infinity. Then each particles should count independent of each other. So this is so-called this propagation of the chaos result. Now, I just want to also talk something about the idea of the proof. And maybe I just talk very quickly about the idea of the proof, since this time is limited. Now here for to prove this result, in fact, we need some uniform bound to obtain the result. And I just mentioned for this psi, we also have the not well-defined terms in the classical sense. So we need to decompose these equations here. We're using this Taprata and Debush trick to decompose this phi to the following two equations, and also decompose this psi to this zi and xi here. And here we can see this mu corresponding to the expectation of this part. We can also decompose it in the following way. And due to this xi and xj, they have the symmetry properties. So this in fact, we can see this. We can write this xi square part to this xj square part. Now we want to prove this yi will convergence to this xi here. Now we just compare each terms with respect to the corresponding expectation part here. And here I just want to mention the blue part is also not well defined in the classical sense. We can see here the regularity is also in C minus, the expectation part. But Zi is also regularities in C minus. But we can using the since here Zi and Zj are independent, we can using the conditional expectation to understand this one. We can write it as a conditional expectation with respect to this Zi part and put this Zi inside the conditional expectation. And the Zi, Zj, we can using the weak product to make sense of it. So we can obtain this kind of result for this kind of model. And now we want to compare the equations. And now it's a nonlinear equations. So we need some uniform estimate. In fact, we can deduce the following two uniform estimates. The main key point is this two red part. This two red part, in fact, it gives us some dissipations. Even if we have this 1 over n, for n becomes larger, the dissipation will become weaker. But if we calculate the average of this yj, the L2 norm of this yj part, we can see this red part will give us this dissipation one. This will help us to obtain the uniform estimate and avoid us to using the Grover's lemma. And for this xi part, we can also using this red part help us to first obtain the L2 norm uniform estimate and later gives us LP norm estimate. And here the important thing is here we need to using the law of large numbers. So we also need the initial data for this psi should be independent of each other. So this gives us a convergence of the dynamics in the two-dimensional case. And now we have the convergence of the dynamics. We want to obtain the convergence of the Mayors. So that means if we know the invariant Mayors for this phi gives by this ON linear sigma model. So we want to see the, so we expect the limit, the larger limit of this ON linear sigma model should convergence to the invariant Mayor for this psi. So first we want to see what is the invariant Mayor for this psi. We write the limiting equation here, we just recall it here. And we want to see what is the limiting equations here. And we can see if now we just assume this mu written in the following way, satisfy these conditions here. If in general this mu should depending on the time and also depending on the space. And if we just assume mu is a constant, so this is just a linear equations. So this we can using the OU, we can see it as the OU process. And we can solve these equations here. And in fact, we can directly use, this is, if we consider its mu is a constant, we can write the invariant Mayor explicitly, just gives by some Gaussian Mayor. It's a Gaussian free field. But by solving this, by using these equations here, we can explicitly write this mu here. This mu, in fact, for two-dimensional and three-dimensional case, due to the effect of the renormalization, we give just this Gaussian free field. For 1D case, this will have some positive mu0 here, satisfy these equations. So we find this Gaussian free field gives one invariant Mayor to these limiting equations. And we want to see whether it should be unique. And in one and two-dimensional case, since here we can obtain if there exists M0 such that M should be larger than this M0, this Gaussian free field is a unique invariant Mayor for this psi. So in here the prove this uniqueness of the invariant Mayor. In general, we have the space-time white noise. That means we have enough noise. So this it should, and we are also in the finite volume case, so that it should be unique. But however, here, as I mentioned before, this is a distributional dependent SPD. The corresponding Markov semigroup is nonlinear. So there are no general theory about the ergodicity result for this kind of model. It's like for the general SPD, we know as a strong failure and irreducibility can imply this ergodicity. But in this case, we don't have such kind of results. So in this case, we just prove the solutions will converge to each other when time goes to infinity. So this will require us to choose this M larger than this M0 part. And now we know this Gaussian free field should be the invariant Mayor to this limiting equations. Now we'll come to the convergence of the invariant Mayor. We also recall this ON linear sigma model here. We use it we use this nu n to denote it. And nu is the corresponding Gaussian free field. So this just means if we consider n equals to 1 without this nonlinear part, it's a corresponding Gaussian free field. And our result, main result in this case is for two-dimensional and three-dimensional case, we can obtain here this nu ni corresponding, if we consider this nu n, the state space for this nu n will also change when n goes to infinity. So this nu ni just means the ith component of this nu n, just we consider as a stationary distribution of this each phi I here. And then we can prove this new Ni form a tight set in this probability measures for the probability measures on this holder space. This is for the 3-dimensional case. For 2-dimensional case, it's only in C minus kappa space, it's better. And furthermore, we want to prove the convergence of the measure. And we can obtain, if M is larger enough, we can obtain this new Ni will converge to this Gaussian free field. And the first K component of this new NK will converge to this product measure, this new cross this new here. And we can also obtain the convergence rate. Here, this W2 corresponding to a Wasserstein distance here. And we can obtain the convergence rate given by this n to the power minus 1/2, just given in this way. And here, this kind of result can be also seen as like this mean field kind of result for the measure. And this convergence rate is expected to be optimal convergence rate in this mean field theory. And here, in fact, first when we want to prove this kind of result, we first want to using the convergence of the dynamic to prove the convergence of the measures. But we meet the difficulty. The difficulty is that here we don't know whether each component of the tight limit is independent of each other. And here, since the limiting equations will have the nonlinear semigroup, Markov semigroup, so this property also does not hold. This is in general, we can change a random initial data to a deterministic initial data. But here in this case, we cannot using these properties. And we also try to control the nonlinear term, but it seems not easy to control this nonlinear term when to make this time goes to infinity, since here we have different components. So instead, we give some just idea of the proof. Now we just want to prove the convergence of these two measures with respect to this Wasserstein distance. So the idea is just we take the first by your definition of this Wasserstein distance, we need to find a coupling between these two measures. And the couplings between these two measures is just given by this. We know phi I will have this new Ni as the invariant measure, and the Gaussian free field gives the invariant measure for this OU process. So we just take these stationary solutions to these two equations as our couplings. And now we want to prove the convergence of this new Ni to this new. So we just compare this phi I and Zi here directly. So this way, and we just recall by using this trick, we do the decomposition, we get this Yi here. And now the right-hand side, the red part is the worst part in the equations. The regularity is in C-1 minor space. Now we want to get some uniform estimate for this Y we want to prove this Y will convergence to 0 to obtain our result. And here we can see, in fact, the best regularity for this Y, in fact, is only in C1 minor space. So if we want to do the uniform estimate, like the energy estimate, we can see this red part will defined in the classical sense. So here, this notation is like some pair product. And also this part, if we consider Yi, the best regularity is in C1 minor space. But here we need the H1 norm of this Yi. So this one is not well defined in the classical sense. And by using this pair product decomposition, these two terms are also not well defined in the classical sense. But by using the idea from this Gubinana and Hoffmanova's paper, we know there's cancellation between this pair product. So each of these terms are not well defined in the classical sense. But if we take the summation with respect to I, we will find all the bad terms will cancel to each other. And we take summation, we can get some better regularities. In fact, this will give us a following uniform estimate here. That means we can obtain the following uniform estimate. And now since here phi and they are stationary, so now we have the following controls. This also depending on the initial data. But since phi and they are stationary, so this y also stationary. So in fact, we can cancel these two blue terms with respect to the initial data. Now we want to get the uniform estimate for the right-hand side, then we can obtain our result here. Because here, if we can obtain some uniform estimate independent of n, now for here we take the sum over n, so we can get our result. The convergence rate is given by 1 over n square root of n. Now the problem is we need to handle this Rn part. This comes from the nonlinear part. And the idea is here we decompose this Rn to the following two parts. This part is Rn minus the expectation part of it. And for this one, this is like if we consider this one, we can use using here this one. In fact, it has this 1 over n, but it also has some dissipations. So for this one, we can using this Holder's inequality to get this R minus expectation of it. We can obtain the square of this one, and we have actual n in front of it. But this Rn can be seen as the independent sum of the random variables. So this is like to calculating the variance of this one. And we're using the, this is like the proof of this law of large numbers. In fact, we can obtain, even we have an extra n in front of the coefficient, but this one is bounded uniform in n. And for expectation of this one, we can choosing this m large enough to absorb it. This is also a reason here we need this m large enough here. And we can obtain this result. So this is for the convergence of the Meyers here. And here recall this result. When we can obtain the convergence, this new n, in fact, will convergence to this product Meyer. That means this nonlinear term will not have the effect for the equations. So in the quantum field theory, we also want to study some observables to see some non-trivial effect from this model. And we studied the following two observables. So if we assume phi just have the random variables having the law given by this new n, then we can consider the following two observables. This is like to consider the fluctuation of this phi square and also consider the square of this first two observables. And we can obtain the first one is tight in this base of space. And for three-dimensional case, the space is even worse. And the second observables we can obtain for two-dimensional case is also tight in this space. And furthermore, if we consider the limiting of these two observables, we can see the limit of these observables are not the same as the corresponding observables for the Gaussian free field. So that means, as we the previous result, we know for each phi I, it should converge to this zi in distributional sense. So phi I square should also converge to this zi square. But if we take some summation and do this kind of scaling, and also do this kind of scaling, we can see the limiting are different. So this gives some non-trivial effect from this field. And to prove this kind of result, in fact, we calculate the correlation functions of the first observables and calculate the expectation of the second observables. And to calculate the correlation or expectation, in fact, we're using the integration by parts formula, or so-called this Dyson-Stringer from this Cupianis. Our motivation is from this Cupianis using this integration by parts formula. In fact, we can change the correlation. This integration by parts formula gives us relations between different weak powers. So we can using this to change the correlation part or the expectation part to the main part and some error part. And for the error part, we can using the SPD SPD estimate to obtain following estimate by using the independence. And this makes us to prove the error part goes to 0. So finally, we can obtain the correlation part and the expectation of the second observables are different from this one. So this gives us the limit of these two observables should be different from this Gaussian free field. So this is our main result for this observables. And maybe the last slide is for the problems for this, for the problems for related to my talk. First, we don't obtain the convergence of the dynamics for the three-dimensional case. And also related to this observables, we also don't obtain the correlations for the three-dimensional case. So here, but for the two-dimensional case, we can obtain such kind of regularity estimate. But three-dimensional case, we need more regularities. So we need to do more to obtain such kind of result. And another problem is how to drop this condition, like for this M is large enough condition. Maybe here we need to develop some general theory on this distribution dependent singular SPD to find for the ergodicity and to drop these conditions here. And also whether we can do more larger limit for the other models by using the stochastic quantization. And that's it, all I want to say. And thank you for your attention.
Thank you very much, Rongchan, for a very interesting talk. Are there any questions?
Please raise the hand if you want to raise a question. Ben, Tatsida has a question.
Yeah.
I am Tadaisa Funaki.
Hello, hi, Professor.
Yeah. So it's a very good talk. Thank you very much.
Okay, thank you.
I understand that the limit stochastic PD is a kind of a Makin process because mu depends on
yes, depending on
the distribution of the psi I.
Yes, depending on.
So my question is, can you really prove the propagation of chaos? That means psi 1, maybe psi k, you have a joint distribution. That converges to psi 1 to psi k, which are independent.
Yes, I think from here we can already obtain.
You take two terms. Okay, I see. Then in the Makin's case, the limit psi I are independent, even phi I is not. So you can prove that?
Yes, even phi I are not independent, but psi I are independent, so we get this.
Psi I means the initial value, but I mean the process itself.
Yeah, at a fixed time t it should be independent because the initial data are independent, and also this psi are also independent of each other.
Okay, I see.
Component, so they are also independent.
I see. So you can prove the propagation of chaos. I see.
Yeah, yes.
Okay. Okay, thank you very much.
Okay, thank you.
Any other questions? Yeah. I would have a question about this condition that M must be big enough.
And must be big.
Yeah, so this is a well-known, say, difficulty even for much simpler stochastic PDEs. And usually the method is that you cannot work exactly with the drift in the equation that you have, but you modify it, say, locally in some way that you can get ergodicity and even estimates on the rate of convergence. Is it possible to do something similar here? Would you expect it? Or if you take, say, if you take reaction diffusion equation with polynomial drift, that you can then you can modify it locally and you can prove the rate of convergence to invariant measure.
Yes. But in this case, if we just consider for example, if we just consider for the phi I for fixed n, I think this can be, we can obtain the convergence to the invariant measure. This should work for fixed n. But if we just consider the limit equation for this psi I, we need this condition, then we can obtain, under this condition, we can obtain the convergence. Also, convergence rate is exponentially fast. Yeah.
Are there any other questions?
I have a question. The Ben, the M is the potential M is not just a constant. Is it in general a bounded function?
M is just a constant.
Just a constant. I see. Okay.
Yeah.
And there's no chance to get something also MX dependent? Any results? If M would be an essentially bounded function instead of just the constant, but strictly positive, would there be any chance to?
Because to my understanding, this M just corresponding to some mass renormalization. It's like because in the quantum field theory, they just take it as a constant.
Okay,
so
you cannot take it. Yeah. I see. You cannot consider and generalize actually this to general Schrödinger operators.
Schrödinger operator, but if we consider Schrödinger operators, we don't need the noise, right?
Well, with the noise, of course.
With the noise, you just means change M to some functions here.
Yes, exactly.
Then we need some conditions, I think.
Of course, you need additional conditions.
I think maybe it's bounded should be no problem.
I see.
But maybe we also need some regularities to make sense of this M times this psi if it's a function.
Yeah, of course.
Also, yeah.
But I think it would also make sense to study exactly this, not only for the Laplacian, and but also, in fact, for the general Schrödinger operator. You know, of course, where the potential.
You mean have some I, right? Oh.
No, without the imaginary number I. Just maybe later, but this would be maybe another step to add an I, but just for looking for, instead of the Laplacian, looking for the Schrödinger operator.
Okay, maybe, I think it's also very interesting. Maybe, we need to check whether we can find some motivations from this quantum field theory to find this kind of model. Yeah.
Okay. Yeah, well, because the quantum fields model, I mean, the Schrödinger operator is directly related to, actually, you know.
Yes. All right. Okay, thank you for your suggestion.
Any other questions? If there is no more question, then let us thank again the speaker for a very interesting, stimulating talk. And let me remind everyone that in a few minutes we can meet at the coffee break, and the link to this new meeting has been already sent. Thank you very much.
Okay, so I stop.
Yeah. Yeah, thank you.
Okay, so see
Thanks.
you.
Thank you.
Thanks.